top-class problem solver. The goal of this video is to help us learn to analyze the problem and communicate our solution effectively. Two in-phase 300 MHz radio sources are fixed along a north-south line 20 meters apart. A close array of radio detectors is placed along another north-south line 1.5 kilometers east of the sources. What is the location in meters of the detector at the third order minimum? The problem-solving method consists of 3 steps. The first step is interpretation of the problem. Then we devise a strategy, and then we execute our strategy. The first step of the interpretation is to identify the concept embedded in the problem. There are several clues in the wording of this problem that suggest this is a problem in 2D interference. But I think the word that really gives it away is the last word of the question, namely minimum. So we write that this is a problem in 2D interference. The next step of the interpretation is to create the model and represent the model in a diagram. In this problem, we are given that we have 2 radio sources aligned in a north-south direction. We are also told that we have a parallel array of detectors also aligned in the north-south direction, and that this array of detectors lies east of the sources. This is the standard setup for these problems in 2D interference. We have our 2 sources represented as point sources and denoted by S1 and S2. Along the line joining our 2 sources, we denote the separation D. We denote that for the sources, the wavelength of the wave is lambda, and in this problem we are given that the sources are in phase. At a distance L from the line joining the 2 sources, we have our array of detectors. This array of detectors is analogous to the screen found in Young's double-slit experiment. We notice here that the slit separation D is much less than the slit to detector distance L. We will indicate this here. We also show our point of detection, which we call P, and we draw the dashed line joining P to the midpoint of the sources. The linear position of P we denote by the parameter lowercase l, and the angular position shown here is denoted by the parameter theta. Finally, we draw the ray from S1 to P and S2 to P because it is the difference between the lengths of these rays that will determine the type of interference we have at the point P. The third step of the interpretation is to extract the data carefully from the problem. We are told that the sources are in phase, and we're given the frequency of the sources as 300 MHz. We are also told that the sources are radio sources, which is going to be an important fact later on. We are told that the 2-point sources are 20 meters apart, and we are told that the array of detectors, our parameter big L, is 1.5 kilometers from the line joining the sources. So we indicate these parameters in our data. The frequency we will write down directly as per second. Likewise, we will write down our L parameter directly as 1,500 meters. The first step of the strategy is to determine precisely what is required. We are required to find the location in meters of the third order minimum. This would correspond to our parameter little l in our model. The second step of the strategy is to construct the concept map. The concept map relates the parameters that are given in the problem and the required parameter. The concept map may be broken down into two parts. The linear position of a given fringe, given by lowercase l, is related to the angular position, theta, and the screen to slit distance, capital L. Theta, in turn, is determined by the path difference, delta r, and the distance between the slits, d. In turn, delta r is determined by the wavelength of the waves lambda and the order of the fringe m. Lambda in turn is obtained from the frequency of the wave and the speed of propagation of the wave. The third step of the strategy is to create an action plan based on the concept map. Let us first identify our known quantities and the quantity that is required. We are given L, the screen to slit distance. We are given D, the distance between the slits. We are able to determine M from the order of the fringe. We know F and U, the parameters of the wave. We are required to find the linear position L of a given fringe. Let us now work out the plan. From the frequency, we determine the wavelength lambda. Using lambda, we determine the path difference delta r. From delta r, we find the angular position of the required fringe. And from the angular position, we find our required parameter, which is the linear position of the required fringe. The first step of the execution is to follow the steps of the action plan. From our frequency, we will use u is equal to f lambda to find the wavelength lambda. Here we incorporate the fact that the waves in question are radio waves. Radio waves are a type of electromagnetic radiation. All electromagnetic radiation travels at the speed of light given here. So using u is equal to f lambda, we are able to find the value of lambda shown here. At the next step, we use delta r is equal to m times lambda. Now we're not given m explicitly, so we have to determine m from the information that we're given. We're told that we're looking for the third order minimum. So going through our various possibilities for m, we recall that for sources in phase, the first order minimum corresponds to m is equal to 1/2. The second order minimum corresponds to m is equal to 3/2, and the third order minimum corresponds to m is equal to 5/2. So, seeing that this is the minimum that we are required to find, we use m is equal to 5/2, and we find our value for delta r. At the next step, we find theta. We use the approximation for d much less than L, which tells me that delta r is equal to d sine theta. From this, we obtain our value of theta. Finally, from our angular position, we use simple trigonometry to find the linear position L. The second step of the execution is simply to write down and highlight your final answer. So here we write our final answer. Notice that for this problem, we take great care to interpret what L is in terms of the parameters that are given in the problem. The third step of the execution is to check your answer. When you check your answer, make sure that you state clearly what is required, that you give the appropriate unit, and that the magnitude of your answer is reasonable. We check that we are required to find L, the linear position of my third order minimum, and this is exactly the answer that we have provided. We then check that our unit is in meters, exactly as required. We then check the magnitude of our final answer. We use the similar triangles here and here to help us approximate what our final answer should be. Simply put, the ratio of delta R to D should be similar to the ratio of small l to capital L. So we have that delta R is equal to 2.5, which when divided by D is of the order of 1/10. When we check for small l over large L, we see that small l is 200 meters, large L is 1500 meters. This is also of the order of 1/10. So this is a check on the magnitude of our final answer. Here once more are the 3 steps of our problem-solving method. Thank you for watching.